So, we go from the stars here to water. It's just like, gosh, Pierre, can't you make up your mind what you want to talk about? So it's actually because these topics are related because of lattice. So, and hopefully that's the lesson that you'll come to learn as you listen to this talk on the microwave background. Now, I've had the privilege of being a professor at Ohio State. It's a big thing in life to be blessed with such a thing. And one of the professors, but one of the reasons it's such a big thing is you get to meet such wonderful people in a university. Right now I'm on the admissions committee for the College of Medicine, and we get like 8,000 applicants a year. You want to take them all. And there's so many wonderful young people out there. And one thing about a university is you also meet wonderful professors. And so today I'd like to dedicate this talk to an emeritus professor, Robert Bailey, and you'll come to understand why as the talk proceeds. So this talk's on the microwave background. Of course, for most people in the audience, how can this possibly be related to water? And people who know my work understand that I've said that the microwave background actually didn't come from the universe, but actually came from the oceans of the earth. And so this talk is centered on explaining why it is that water can produce such a signal and why it was missed. So we'll begin in 1965 with the great Penzias and Wilson experiment. And even if this signal gets reassigned, I still hold that this was a wonderful discovery, that the Earth was surrounded by a 3 Kelvin signature, a 3 Kelvin noise. And of course, initially, this was interpreted as this 3 Kelvin noise came from outer space. It was a signature of the Big Bang. And then we launched a satellite called COBE, which circled the Earth just 900 kilometers above the Earth. And we got this phenomenal result. I mean, COBE was launched, and I think within a month the paper had been submitted, and this curve was published. But I always had a problem with this curve because the production of a thermal spectrum requires an appropriate structural lattice. This is just as we've talked before with the sun, and now the stars, and now back to the background. So it's not possible that such a spectrum could originate from the universe, from the early universe, because it had no means of producing it. The optimum lattice for the production of such a spectrum is the shared graphite or soot hexagonal planar lattice, but clearly it was not produced from graphite or soot. I mean, this spectrum comes from something, and it wasn't graphite or soot. But I still want to keep in mind that this lattice of graphite and soot as the cause for this spectrum. So the most likely candidates are the oceans of the Earth themselves. Now, this has a lot of consequences for mankind because, of course, if the signal belongs to the Earth, as I'm saying, we really want that signal. I mean, we can't just leave it to astronomy because the geophysicists need it, and people who are studying global warming definitely want to include it in their radiative balance equations of the Earth. So this is an important problem, even though it's a microwave signal and not a lot of energy is coming out of it. When you integrate it over the whole planet, it's a lot of energy actually. So I've published several papers about the microwave background. First, these are papers just about why water could be able to produce this and why the signal could be isotropic. So remember that the Penzias and Wilson signal, the microwave background signal, now I'm talking about the monopole of the background, which is the one that I displayed in this COBE curve, that the monopole of the microwave background is isotropic. It's independent of season, and they couldn't see any directionality to it when they moved their antenna around. But nonetheless, I did reassign it to water, and then I went through and I did some analysis of satellites, the COBE satellite and the WMAP satellite in great detail. I call them radiological analysis because really it's you know, we deal actually with very similar techniques in magnetic resonance. The 8 Tesla at Ohio State was at 340 megahertz, so we're almost in the gigahertz range for microwaves, so very similar techniques. And of course, we're all concerned with image analysis in this data and signal analysis. For those who are interested in it, I did give a talk. I was privileged to be invited to the EU in 2014, and I met a lot of wonderful people there, and I gave 3 talks, and one of them was on the microwave background. And so if you don't know about my work on the microwave background, I just urge you to go to this YouTube of the EU, and you'll be able to hear my lecture on the microwave background. So why is it that that this signal cannot come from the universe? And that is because the universe is not contained in a rigid enclosure. So if you believe that Kirchhoffs' law is correct, which I do not believe, you need to have a spectrum like that. You have to have thermal equilibrium with a rigid enclosure in order to get an accurate temperature. You have to know what the source is. And of course, Penzias and Wilson didn't have that. So the question is, did they have a right to set that temperature? And also, the universe has no access to a structural lattice at the beginning of time, and therefore could not have produced a spectrum. So I'm saying if you have a thermal spectrum, you need a lattice to produce it. And so this spectrum is no exception, and that's why I also have challenged the microwave background. And part of this is related to the sun becoming condensed matter. Of course, if the microwave background gets reassigned to the Earth, then it'll be clear that the sun is indeed condensed matter. There will be no more arguing about it. So the Big Bang is a non-equilibrium process by definition. There was never a thermal equilibrium with an enclosure as required by Kirchhoffs' law, even if the law was valid, which I claim it's not. On Earth, the creation of a blackbody spectrum always requires the presence of a vibrational lattice. Now, it's interesting that water is an excellent absorber of microwave energy, as seen in our kitchens and observed in our submarines. So as soon as the submarine breaks the surface of the water when it submerges, for all those people who like Red October or Crimson Tide, these are great movies. So, you know, as soon as you remember in Crimson Tide, you know, they want to raise the buoy and stuff because they can't communicate, right? So he wants to raise the buoy and then he gets in trouble. So underwater, you can't transmit microwaves. So actually, as soon as I was told by a person who had served at sea for years on a submarine, he said as soon as the antenna tip touches the surface of the water, it's over in microwaves. So clearly water is a powerful absorber, and by Stewart's law, it must also be a powerful emitter. So the problem is, where's the microwave emission from the Earth, and why did it not interfere with the Kobe measurements? And of course, I'm saying that the reason it can't interfere is because you're measuring the Earth. That's why it didn't interfere with itself. And I published a little paper. It's just a very trivial thing. If you look at the water dimer, there's a translinear bond here. And when two water molecules come together in the dimer, you have this, the central hydrogen is shared by both water molecules. It's a hydrogen bond on one side, K1, that would be the force constant for that bond, and the force constant for the other bond is K2. But interestingly, when that, for the hydroxyl bond is K2. Now, when the little hydrogen moves, you notice that X1 and X2 are just the same. They have the same absolute values, right? One's just the negative of the other. So you can write that the energy of the first system, if you consider these uncoupled, you could write that the energy of the first system is 1/2 K1 X1 squared, and the energy of the second is 1/2 K2 X2 squared. Now, K1 and K2 are force constants. We're looking at a spring type of problem. These are the equations for energy in a spring. So we're looking at a spring, and you write down the energy equations, and what do you get? Well, because X is the same in both, this falls out so that you get the energy of the first system divided by the energy of the second is just equal to the ratio of the force constants. Well, we know that the force constant for the hydrogen bond is about 100-fold weaker than the force constant for the hydroxyl bond, and therefore the energies are 100-fold different. So that means that if you're getting emission in the infrared in the hydroxyl bond at 300 Kelvin, the other one will be giving you emissions at 3 Kelvin. So in order to obtain a thermal microwave spectrum, it takes more than the ability to absorb or emit microwaves, however, right? Because I'm talking that the material involved must be able to emit all the required frequencies, and that involves a suitable structural lattice. So now we need a structural lattice in water. Now, if we go back to Kirchhoffs' definition of a blackbody, it's very interesting when he was working back in those days that he did realize that when he built his box, he tended to coat it with soot. And he made this observation that the investigation will be very much simplified if we imagine the enclosure to be composed wholly or in part of bodies which, for infinitely small thicknesses, can absorb all rays which fall upon them. So he knew that even a small layer of soot could render this thing to be a blackbody. Okay, it doesn't take a very big thickness, and that was known in 1860. So I've mentioned that graphite and soot are unsurpassed in their ability to act as natural blackbodies in the optical range. In part, this is the result of electron delocalization over these ring structures, which enables the conversion of vibrational energy to light and vice versa. So if you note that just even a single layer of graphite, which is called graphene, just a single layer, okay, and this is a quote from a paper, despite being only 1 atom thick, graphene is found to absorb a significant fraction, 2.3%, of the incident white light as a consequence of graphene's unique electronic structure. So just think about that. You just got one layer here, and you already can absorb 2% of all the light. So, 45 layers of atoms, which is a nothing, you can absorb the whole thing. It's really remarkable. And if you look at the electron distribution in graphene, soot, and graphite, this is what it looks like now. I've simplified the diagram. So in graphite, each carbon is sp2 hybridized and is bonded to 3 other carbons. Only 2 are displayed here at each loci. At each vertex, there's only 2 carbons that are displayed bonds to 2 others, but there's another carbon that I didn't draw just to keep it simple. So, and then 1 electron can be placed in each empty p orbital. These lone electrons actually end up being delocalized over the entire structure. This accounts for graphite's excellent ability to absorb and emit light. So in liquid metallic hydrogen, the formation of metallic hydrogen results in the delocalization of all electrons in conduction bands. These then act in the generation of light as the proton lattice of the photosphere vibrates. The interproton distance is ensured by the need to maintain proper quantum conditions to support electron delocalization and conduction. In the photosphere, the interproton distance is such that one has a semi-metal like graphite, which is not fully conductive. So here's a picture of the Earth, and I've shown this picture before, and you see there's an awful lot of water there. So now if you look at the structure of ice, it's interesting that ice also has a hexagonal structure. It's present in ice, but it's not planar. So if you look, you'll see the chair conformation for people who have taken organic chemistry. On the figure on the right, you see 3 chairs at the top. If you follow the little dashed lines and you only concentrate on the top of the figure, on the right side, you'll see 3 little chairs side by side. So they have a chair structure. Now the problem with this structure, of course, for our purposes, is that the p orbitals are not going to be lined up appropriately to have resonance structures ever. So the hexagonal structure is present, but it's not planar. The electrons cannot be delocalized over the rings to allow for strong absorption in the optical range, as seen in graphite or soot. Now, but what is the structure of water at the interface? Well, it turns out that people had, in the 60s, and I think maybe in the 50s, people were starting to think that water at the interfaces are different, and most of you will know that Jerry Pollack's work centers on this. And there was a paper published in 1969 on polywater, and this is the structure that was proposed. And note that in this case, we are now dealing with H3O2. As such, and there should be a little minus sign there, I think. As such, the hexagonal planes carry a net negative charge, while the net positive charge must be transferred to the adjacent environment away from the interface. So you can get these. So polywater, they propose that this structure could exist. But the idea that liquid water can can adopt the hexagonal structure at interface as proposed by Lippincott and all for polywater has been largely dismissed by the scientific community. The first key retraction of support for the idea came in the form of a theoretical paper published in the journal Nature, which I cite there. And no mention of the structure can be found in modern science textbooks on hydrogen bonding in water. So you just have to be aware of this, that no respectable scientist on water will tell you that such structures exist. So, and then we come to Jerry. Now, a lot of you here probably know Jerry, and I think he's a really capable scientist. And he wrote this book, The Fourth Phase of Water, and it's a wonderful book. And he's advocated that water can indeed adopt the hexagonal structure at interfaces. And if you want he's got a talk, it's short, a TEDx talk that he gave on the fourth phase of water. It's a short talk, but it's very beautiful. It's got nice examples of water's amazing behavior. So remember, this is the electronic structure in graphene, soot, and graphite. So how about it in the hexagonal structure in liquid water? Well, since we're dealing with H3O-, I just took part of the structure on the left just to localize where the electrons are. So the electrons that had originally come from the oxygen are in red, and the ones that came from the hydrogen are grayish. In total, you'll see that there's 16 electrons in this structure, and such subunits can be made to make these hexagonal planes. And in this case, you have 2 electrons in the free p orbital. So when dealing with H3O2-, the oxygen atoms are sp2 hybridized just like in graphite. But now the 2 electrons are in empty but now there are 2 electrons in empty p orbitals. Also, the p orbitals are too far spaced to allow for delocalization. The protons are surrounded by 4 electrons. The structure, while not conducive to optical absorption because of lack of delocalization and bond lengths, should nonetheless be able to permit microwave absorption and emission. So what if this lattice might exist which might exist at the surface of water? What happens if this would be compressed? Well, if it's compressed, one might expect excellent absorption in the optical as the electrons become delocalized and the bond lengths are shortened. So the question is, can the surface of water become optically black on compression? That's what I want. I want the surface of water to become optically black when you compress it. And if you could get that, if you could demonstrate that, then you could say that, yes, the surface of water does have this, can adopt this structure. So now we get back to Dr. Bailey. Dr. Bailey is just a great guy. And when I was working on doing the 8T, he actually helped with the table design. He was a mechanical engineer. And he was an elderly professor, and I really liked him. And he came up to me one day and he says, Pierre, you really got to read this book on the effects of nuclear weapons. This is in the mid-90s. And I said, who wants to read about the effects of nuclear weapons? I mean, it's such a sad topic, and the back of the book is just terrible. But, because Dr. Bailey was so nice, and of course he was my senior and a collaborator, and he really wanted me to look at the book, out of courtesy, I decided to read this book. And it's one of the most important books that I've ever read because it gave us the answer that we're seeking today. So what happened was I had read the book, and when I read the book, I read this paragraph in around 1995. And I always remember this paragraph in my head, and I was looking for this paragraph again. Well, Dr. Bailey had retired, and he had moved all his books, so he didn't know what book he had lent me and what it was called. So 4 years ago, I had asked him, really, can't you ask Adrian to look for the book or try to find it? He says, well, Pierre, it's all in my stack of books, and us old professors, we have so many books. So then I go to Germany to meet Dr. Unziker, and we start talking about this. And when I came back from Germany last month, I called Dr. Bailey up again. I sent him an email, and I said, remember that book? Do you think you might look for it again? And then he wrote back to me, and he says, you know, I don't know whatever happened to that book on the effects of nuclear weapons. And then I thought to myself, I bet it's called The Effects of Nuclear Weapons. So Google came to the rescue. I typed it in and found the paragraph. So here's the important thing, is that when a nuclear explosion goes off underwater, this is what happens. In the course of its rapid expansion, the hot gas bubble, while still underwater, initiates a shock wave. Intersection of the shock wave with the surface produces an effect which, when viewed from above, appears to be a rapidly expanding ring of darkened water. This is often called the slick because of its resemblance to an oil slick. So now, we're going to look at it. So, I called the national security for permission to use these videos, which are in the public domain, but my son changed them slightly to slow them down. So here you'll see the blast, and there you already saw that it was blackened. Now it'll repeat here in slow motion so you can see it. We'll show two of these and then we'll... All right. So you'll see it'll detonate pretty much at the center of the screen here. There's the blackness. Now you have to slow it down a little bit, and I'll do that for you. So here we go again now, just at 1/10 speed, and now you'll see it very clearly. See, it's starting. There you see the blackness around in front of that white circle, which looked like the slick. So this comes from the National Security Archives in Washington. Okay, now I'll show you another one. And this is a view what happens from the coast. So you'll see the palm tree move and see the blackness come across, and then the shock wave hits the tree. Now this is at 1/5 speed. So you have an air pressure coming across the sea, and it causes the sea to turn black. It's a sad thing that I have to use this in my science. But anyhow, so now we'll go back to the talk. So there's the first one, seen from above. And here's an example seen from the coast. Now, interestingly, we've also shocked water in the laboratory, and we find that water is transparent at shock pressures up to 30 gigapascals. Now, of course, this isn't the water is completely enclosed here, and then we're going to detonate a device that'll compress the water. But if you go to pressures of 50 to 80 kilopascal, water becomes optically black with an emissivity of 1. So it behaves exactly like a black body, and temperatures up to 5200 Kelvin can be measured. So we can measure those temperatures because water is now optically black, so if we measure the emission, we know what the temperature is. And it's also interesting that the brightness temperature of water increases just with wind speed. You'll get about a 10 degree for a 10 degree increase in temperature. Okay, I'm sorry. We'll go back. If you look at the sea in the microwave, if you look straight down on it, the sea looks like it's at about 100 Kelvin. It's much too low in temperature. And then for the horizontal component, as you move to the horizon, the emissivity drops so that the temperature is going towards 0. In the vertical component, it goes up first and then drops rapidly to 0. But if there's wind speed at 19.34 gigahertz in the microwave, the wind causes an increase in brightness temperature of the sea as you for every about 30 miles an hour, you get a brightness temperature of about 10 degrees. So we also know that the conductivity of water increases dramatically near 12 gigapascals. And in order to account for this, scientists have called for the formation of hydroxide or hydronium ions, but these experiments are devoid of the Raman signature that's needed for such ions. So the possibility that conductivity increases as a result of the formation of graphite-like semi-metal does not appear to have been considered. Now, you might ask, well, what do the other materials do that transparent materials that you might shock compress? So if you shock compress benzene, polybutene, and polyethylene, they all start looking like black. Well, not all start looking. Benzene's not very efficient, but polybutene, it ends up having an emissivity of 1. So just like water. Well, how's that happening? Surely it doesn't have the structure of graphite. But what happens is when these things are shock compressed, you create pure carbon compounds, so you're making graphite in your experiment. So that's why you're getting a perfect emissivity, near perfect emissivity. So in conclusion, it's impossible that the monopole signal of the microwave background arose from the universe. You need a lattice to create it. The signal is very, very powerful near the Earth. And as you know, when you are driving your car away from your town and your favorite radio station is on, the farther you get away, eventually you lose the station. So if you have a powerful signal, so much signal to noise, you're near the source. To put that much power in the universe is just not reasonable. And also you don't have a mechanism. Water has the ability to absorb and emit in the microwave, so where's the Earth's signal? Optical measurements in water during shock compression demonstrates that water has the ability to absorb much like graphite in the optical range with an emissivity of 1. As such, the surface of the oceans are very likely to possess a hexagonal planar structure, much as proposed by Lippincott et al. In 1969, and also, as now advocated by Jerry Pollock. So I think Jerry's on the right track. And one of the things that Jerry has in his book, he has a figure where you see he's looking at Brownian motion in the book. I didn't include the figure, but he's looking at Brownian motion. And he sees that outside of his easy zone, he gets more Brownian motion than inside the easy zone. And I explained to him that he maybe already understood that this is because you have intercalate. So the atoms are restricted to intercalate regions in his easy zone. That's why there's not much diffusion, not much Brownian motion when he's looking at it. So the oceans of the Earth are likely to have... So I think Jerry's doing magnificent work, so just do that on the side because he sure gets attacked a lot. The oceans of the Earth are likely to have at their disposal the ability to produce the thermal spectrum of the microwave background, which can account fully for the monopole signal of the background. God bless you. Thank you for listening to me.